Today we will discuss the projections of product spaces. In the last lecture, we have discussed projections of product space of two topological spaces. Today we will continue the topic and we will also discuss the product of any finite number of topological spaces and their projections. Now, first we shall prove a theorem. Let xt and yv be two topological spaces and x cross y w be the product space. Let y naught be a fixed point of y and let a is equal to x cross singleton y naught. Then the restriction of pi x to a is a homeomorphism of the subspace A of x cross y onto x. Here it is given that y naught be a fixed point of y. So if we take x cross singleton y naught, then this is clearly a subspace of x cross y. And we know that projection pi x is a mapping from x cross y to x. So if we restrict this pi x to this subspace A, then we have to prove that restriction is a homeomorphism. Let us prove this theorem. Let gx be the restriction of pi x to A. That is, gx is a mapping from A to capital X and it is defined as gx of x comma y naught is equal to gx of pi x of x y naught. Because we are restricting pi x to A, so image of gx, image of any element under gx is same as the image of that element under pi x for every element of A. So, and any element in A is of the form x comma y naught. And we know that pi x of x y naught is equal to x. So, we can define here gx for every element of A. And we have to prove that gx is a homeomorphism. That is, we have to prove that gx is 1 1 on 2. This is continuous and it is an open mapping. For x1, x2 in x, let gx of x1 y naught is equal to gx of x2 y naught. Means we are taking two elements and we are assuming that their images are equal under gx. But by definition of gx, we have x1 is equal to x2. Here image is x1, here image is x2. So we have x1 is equal to x2. But this implies that ordered pair x1 comma y naught is equal to x2 comma y naught. These two elements are equal, which implies that gx is 1. Then we shall prove that gx is onto. So take some element of the codomain. Suppose here we are taking, suppose x belongs to x. Then there exists x y naught in A such that gx of x y naught is equal to x by definition of gx, and which implies that gx is onto. We know that restriction of a continuous mapping is a continuous mapping, and we know that actually we have proved earlier that pi x, that is projection, is a continuous mapping, and so restriction of this continuous mapping is continuous, and we can say that gx is continuous. Now we show that gx is an open mapping. Means we have to show that image of any A open set is T open. So let V be any open set in A. Then V is of the form A intersection U, where U is open in x cross y, because A is a subspace of x cross y. So any open set in A is of this form. where U is open, and we know that E given by G cross H, G belongs to T, H belongs to V, is a base of the product topology. We have proved earlier that this is a base, um, and with the help of that base we have defined the product topology. So we know that this E is a base of the product topology W, and so any open set in X cross Y can be written as union of some members of this collection. So take some sub collection E dash of E such that union of members of E dash is equal to U. Then we take Gx image both the sides, then we have Gx of V is equal to Gx of A intersection U, and U can be replaced by the expression here. So we can write here, and then, and since intersection distributes over union, so we can write here Gx of union of A intersection G cross H, where G cross H belongs to E dash, and then A can be replaced by X cross singleton Y naught intersection G cross H. Here we have replaced A by X cross Y, and then here by set theory we can write here X intersection G cross singleton Y naught intersection H, and then we can write here G, since G is a subset of X, so X cross intersection G is equal to G. So here we can write G cross Y naught intersection H, and if Y naught doesn't belong to H, this is a subset of Y, Y singleton Y naught is a subset of Y, H is a subset of Y, and but if Y naught doesn't belong to H, then for every H here, for G cross H in E dash, if Y naught doesn't belong to H, then here we have phi empty set, and we know that cross product, in the cross product, if one of the sets is empty, then the whole set is empty. So this set will be empty, and so we here we get Gx of V is equal to phi. And if Y naught belongs to H for some subcollection E dash of E double dash of E dash, such that Y naught belongs to H, then we can write here union of Gx of G cross, here we have intersection, in the intersection we have singleton Y naught for G cross H in E double dash. And we know that by definition of Gx, its image is G because G is a subset of X. So here we have G, and since each G belongs to T, so their union is also in the topology, and so this belongs to T. So we have shown that image of any A open set is T open, so Gx is an open mapping, as Gx is 1, 1 on 2 continuous and open, so Gx is a homeomorphism. So far we have discussed product of two topological spaces. Similarly, we can define product of n topological spaces, say x1 t1, x2 t2, xn tn. And that product is denoted by product of xi varies from 1 to n. And similarly, we can define n projections by I from product of x1, x2, xn to xi for every I is equal to 1, 2, 3, 4 up to n. And this is defined as pi I of x1, x2, xn. Any element of the product is n in this form, x1, x2 up to xn, n tuples. And pi I will be mapping from this product to xi, so this will give the ith coordinate, and so here we have xi for every I is equal to 1, 2, 3, 4 up to n. and for every element of the product. Now we shall prove a theorem. Let x1 t1 x2 t2 up to xn tn be topological spaces and y be some other topological space. Then a function f from y to this product space is continuous if and only if for every projection pi I, the composition of pi I and f, which is from y to xi, is continuous. Since y and since f is a mapping from y to the product space and pi I is from product space to xi, so we can compose these two mappings and we get a mapping from mapping pi I o f from y to xi. We have to actually we have to show that f is continuous if and only if this composition mapping is continuous. Let us prove this theorem. Let f be continuous, and we know that any projection is continuous. So pi I is continuous, and we also know that composition of any two continuous mappings is also a continuous mapping. So pi I composition f is a continuous mapping. Conversely, let pi I of f from y to xi is let this be continuous for each I is equal to 1, 2, 3, 4 up to n. So we have to prove that f is continuous. So we take some open set here and suppose G be any open set in xi, then by continuity, since this is continuous, so this is pi I o f is continuous, so inverse image of G under pi I o f is open in y, and but we know that this is equal to f inverse composition of pi I inverse of G, so this is open in y. And this is open in y, and we also know that pi I inverse of G is a basic open set in the product space. This is open, and inverse image of this open set under F is open in Y. So it means inverse image of any open set is open in Y under F. So we can say that F is continuous.